Hello friends, today we are going to discuss the bonus video, so I'm very excited here. So today we are going to patch the EXE code using assembly language in order to reduce the enemy's health in 50% in one click, and not to reduce player's health when enemy shoot the enemy player. That means when you click the button in the enemy section, you want the player's health won't reduce, but if you click the shoot button in the player's side, the enemy's health get reduced by 50% in each click. So without any further ado, let's get started. Alright, so here's my desktop, and as you can see at the very first side, you can see there are multiple flight EXEs around here. So those are the versions that I followed. So this is our version that we discussed last week. So you can see the health of the enemy gets reduced, and also the player's health also reduced, and as you know, it reduces quicker than enemy's health. So this is what we have right now. So, and this is what we are going to end up with. Now this is the version number 6. So this fighter 6, and if I click to the shoot in enemy side to player, you can see the health won't reduce at all in the player. On the other hand, if I shoot to enemy, so you can see the enemy's health get reduced 50% in this click, and if I click again, another 50%, and if I click this one again, another 50, 50, 50, 50, 50, 50, 50. Now there's no health here. So eventually it reduced to 0 because we are using int32 or 32-bit integers. So no floating point numbers stored here. Therefore, the value gets 0. Yeah. Any time after we click sometimes, right? Sorry. So this is not any coding done in the C language. This is done purely in assembly level. We patched the executable in assembly. No C++ coding involved here at all. So let's get started and let's see how this can be done, right? So I'm going to open our first version. Let's move all the other versions to a folder. Right now I am end up with this file, right? So if I open, you see the normal behavior is there, right? In order to do this, first obviously, and we need to find the pointer to the, in this case the pointer to player will be suffice. So we have to find the pointer and what is the instruction that affect to this memory value. So I'm going to fire up cheat engine. Yes. Move this aside. So fighter EXE, so open the process, and there is associated table. You can see the pointer is here. So okay, let's do very beginning. So let's remove everything here. Let's start from ground up. All right. So last week we found that this enemy's health is start from 200 and player's health start from 100. So since we know the value, we can directly input those. So now I'm interested in player side, so I'm going for 100 here. So 100 for scanning and shoot, and it is 99 now because it's reduced by 1 by 1. So definitely I hope that this is not the value. The first one may not be the value. Let's see. Some funny reason the first one is the value 2 this time. Alright, it's okay. We found the value, and if let's reduce this and see whether this is the actual one. Right, this is the actual one. So I'm going to reset it to 100. Right now it's 100, and I'm going for the instruction that it writes. All right, so I'm going to need this instruction here. All right, move move EDX. Sorry, move ECX to the content of EDX. So this is the instruction that we came across last week also. So I'm going for the, now I'm going to find the pointer. So in order to do that, I'm going to double click this and copy this address. So this is the base address for the class. So as we know, this is a class, it's an object of a class, enemy and enemy and player, as we discussed last week also. So I'm going to scan the memory address by using hex. So this is my address. So if I double click this one and I copy this value and make it a pointer and I paste this, I get this 99. So anytime I close this and open this again, it remains the same. Let's see. Okay, I open this one again. Yes, so notice this is, so notice this value is no longer here. Now this is there. So sorry, this is our static pointer. Now we found the pointer, and since we are patching using assembly language, we need to know about this instruction too. So if I show it in this assembler, you can see there's nothing. That is because now the mapping of this executable has changed. So the earlier memory locations are no longer valid here. All right. So therefore, I need to go another round here, find what writes to this address using the F6 key or whatever. So I'm going to find what instruction that writes. So this is my instruction, right? So it's there now. So if I show this is in assembler, I can see this one also there now. The offset of the instruction that lies relative to the base of the module address. Now we are going to patch the code right from here. All right, we are going to patch the code right from here. So therefore, I'm just going to copy everything. Oops, all right. So I'm going to copy to clipboard bytes and opcodes. Yes, just use the opcodes. So this is everything. So I'm going for my notepad here. So I just paste these, right? So I have this 11b2 is move EDX, and these are here. Now this program, let's keep this program like this. Now we are going to another editor, or rather assembly editor, that is OllyDbg. I will put the link in the description to download this OllyDbg binary. So we use this to actually edit the assembly code inside the executable. So I'm going to double click this and click OK here. So here I'm going to open our executable file. So it's in desktop. The name of the executable is fighter. So this is the one. So this is the window that we are going to focus, right? This is the assembly instructions. This is the window that we are going to do the editing, right? Now as you can see, when you check the title, it says fighter EXE and CPU is main thread, but the module is not the module that we want. The module is kernel. We are not going to edit the kernel code here, so we have to change the module. So for that I am going to press Alt and E. So When you press Alt and E, this window pops up and displays all the modules loaded with our executable. So as you can see, we have in the top, we have this module. As you can see, the memory address base is 1C0 to 120. So this is the base address of this module. This is the module of interest. So you may wondering why the CLR is loaded and .NET framework is there. That is because, as I stated earlier also, we developed this program using C++.NET. So since this developed in C++.NET, the CLR or .NET framework also loads. So I'm going to double click this first entry, that is the module that we are interested with. So here my module is 1C1000. So when we click Alt F, Alt E, you can see my module is 1C40, right? Now if we go back to our cheat engine, you can see after the base, if I add 11B2, I can get to this instruction, right? So here our base is 1C 4 and 4 zeros. So basically the address now will be, our address in our OllyDbg instance is 1. If I use the full address 001C 12340, right? And if I add 11B2 here, so if I add this address, it resolves to 001C 11B2, right? So in our OllyDbg program, let's head down. So as you can see, when we travel to that offset, we can find that address. So if we scroll up a little bit, and in OllyDbg, cheat engine also, if we scroll up, you can see this push EBP, and these instructions are same. So this from here to right here is a method. In assembly, method are represented like this. You can easily find the methods in assembly language by using these two entry sequence and this exit sequence. Basically, this this move creates a new stack and set its pointer to the current stack. So basically it pushes the EBP, so base pointer pushes to the stack and saves its values, and ESP is gonna move to EBP. So EBP now points to our top of the stack, because ESP the stack is created in ESP's address. Now EBP is also pointing to the ESP, so both are points to the top of the stack. So now we have a stack. So if you have local variables, there will be another line called sub EBP or sub ESP or EBP by, let's say, 408. So if you have 4, there will be a 132-bit integer in your method. So it's a method local variable. That's why you cannot access method local variables after the method calls, because this EBP allocates the memory by subbing EBP, or I think it's EBP, subtracting EBP for some amount of value. After that, it's gonna move back EBP to ESP, so everything going to be destroyed here. So in this case, basically it seems like ESP is the one who allocates the memory, and EBP is going to move against to ESP. So the allocated space is gone now, and pop the EBP, this instruction, and go back. All right. So patching in assembly is easy. It's a easy task. It's not that rocket science, so it's not hard. But most important thing to remember is you have to keep track of these push pop instructions and also this flag register, right? So so if you push, you have to pop. So here you pushed and you popped it, right? So also you have to be very careful with these stack registers. If you misalign the stack or corrupt the stack, your program gets crashed. So let me, for example, if I remove this pop instruction, instead I replace with nop. So if I save this, so I'm going to right click and copy to executable and selection. So I save and I create another version. So let me rename this as fighter underscore crash. So if I run this, oops, I don't know what's the correct one. So yeah, this is the correct one. So this is going to be crash because your stack is no longer working properly because it's misaligned now. So when some other instruction pop from the stack, it will encounter some other value from the stack, so it's gonna crash, right? So let me reset this program here by using Control and F2 and click yes. So I'm going for the module again, so the same address here. I'm going to jump now. In order to patch, what we are going to do is we create a diversion from here to some other location and then do the calculations or comparison or whatever, or health reducing, health increase or whatever from here, and come back to this location, or rather after the jump, and execute the let the executable to execute as it execute normally. So here I'm going to add a diversion from right here. So since we already copied the instruction, so these are the instructions that we require. So here this says move ECX to the contents of the EDX, right? Contents of the EDX in the data segment. Oh, that means your RAM, right? So in most of the executable files, in the bottom of this executable, we have empty space that we can add code. So here you can see this add byte ptr ds to ex with AEL. So this most of the time these instructions not get called because there will be no call instruction to these places. So let me page up here. So this is the code that we have right now. After this code, we have this bunch of add byte ptr ds to ex and al, right? So I go 10 or 20 bytes right here, because if the dynamic code allocator fills this address, there should be a space to do that also. So here I'm going for 01C4. let's go for this one. This should be clean because this new address it starts from 800 and there is double zeros, so that would be good. So now our address is 001C4800. so let's calculate the offset and save it either also. So our base is now 1C and 4 zeros. This is 1C 4800. Now our new code address is plus 4800, right? Now I'm going back to our original code, and from here I'm going to add a jump to our newly found location, that is 4800. So I have to enter the full address here. So 001C and 4800. So I jump. Notice it ate all the instructions below. That is, this instruction costs much higher bytes than the instruction that was earlier. So this instruction costs this byte obviously, and these bytes also. So now in the jump section, after we do the jump, we have to manually enter these ones also. That if we didn't do it, this is going to definitely crash the stack, because there are instructions that involve in the base pointer and the stack pointer, and there is also a pop instruction that should be reversed to this instruction, and this moving also should be reversed. That's known as standard exit sequence. This is known as standard entry sequence. So basically we need to reverse the standard entry sequence by using standard exit sequence. So here we just add the exit sequence. So for this, now as the first version of this file, let's add the diversion and add these instructions to that our diversion, and let jump back to this ret. So it will be 11B7. So if I press enter here, you can see it jumps to this location. Now if we save and run this, the executable file definitely gonna crash. So here I'm going to use the same instructions. So I'm just using plain old instruction set. Nothing here, nothing fancy, just copying and pasting the previous instructions. So to check our diversion is correct. Alright, I'm not, you see there is also a ret instruction here. Now I'm not going to use the ret instruction here, or I can use from here also. But since ret instruction is already in our previous code, I'm just going to jump to that location from this location right here. So let's get our ret location. So ret is in 11B7. So here is also 11B7. So I'm going to jump back to 11B7 from here. Alright, so now I'm going to add another jump here. So this jump is very important. We have to jump to 11B7 in this instance. When we do anything, we have to jump back to 11B7. So here now it's going to be 001C. Now it's 11B7, right? So oops, right. Now if I press enter here, you can see it just jumps right back to our ret instruction. So if I enter here, I get jump and do the work here, and I do the standard exit sequence, and I jump back, and it's gonna return. Alright, now this jump instruction does not harm the registers, the flag register. So we don't want to push save any registers here. We just jump back and forth here. So jump here and jump back. So no change in the register value. So no, now at this moment we don't want to worry about that much. The stack and the flags registers, right? So with this modification, let's see our diversion work correctly or not. So I'm just going to play right from here, and I have another instance, but I'm not sure what is the correct instance. I believe this is the one, because other one looks like I closed it. Okay, let's start this one again. I believe it cannot be started. Okay, why don't we copy the instructions to the executable and save it and try that one again. So I'm just going to right click, copy to executable and all modifications. So I copy all, unable to locate data in EXE. I believe the problem here is and the exe file is already executed and closed, so I have to load this one again. That is because the process is killed at this moment. So here let's see now. Yeah, same location. So I'm just going to add a jump here, so I have everything I need. And if I jump here, so I have the correct address and I jump back, right? Now it's working. So I copy to execute to go the all modifications. Right, now you see this message. That is because the data section that we added is is allocated dynamically. So we have to find another address that won't damaged with dynamic allocation. So this is kind of trial and error situation. So let's go for this address. So here let's try to so you still cannot allocate the data here. So let's see. Right now it seems that these things can be copied. All right, so yeah, we have a bunch of data that we can use. So this is from here to here we can use. So these jump divert PTRs are mapped to right here in the section jump divert PTRs, right? So from that we have this is 3B9C2, so 3BEF, right? 9C2EF. So if I check image here, so this is our, so from here right from right here in this location we don't have anything. So if I can find another location, so here you also have this. So if I go to image, I believe it's in the data section. So this is not this area, right? So we have this to, from here to here we have we can do anything, right? So this is kind of trial and error. So let's add the instruction to that location and let's see what we can do. And right, still those are in here, right? So so this is the last address that I can go for, right? So I immediately start from right here. Okay, all right, let's start from here. 47A0. Now, like previously, I'm going to let's reset the program once again. So go to the module and fight, right? So here let's go to our location. Here I'm going to, right, let this location stay right here. So if I go for image, so I have C47A0. so this will be our new instruction. C, now it will be 47A0, right? Now 47A0, right? Now I'm going to just copy the instruction to the 47A0 here. So this code size can be increased using a PE editor, but you have to do it carefully because you have a chance to corrupt your executable there. So you have to do it very carefully. So I'm going to jump back to 11B7. (001C) and paste this, and I have a jump, correct jump here. So from here, from this address onwards, I'm going to jump to 47A0. So JMP 001C. Now I'm going to copy the address, right? So for 7A0, right? Now still I have the same thing. Okay, I have jump and right now. So I'm going to copy the all modifications. I'm going to copy all. So now nothing, no errors happened. Now it copied. Now I'm going to save this by clicking yes. Now I'm going to rename this as fighter EXE and with diversion. So I have the code diversion here. So let's see the diversion. Now here I have this. Let me close this one, otherwise it's gonna mix up. So this is diversion. Let's see whether this one works. So you can see no funny thing here. It works like the previous one. So no big deal, right? No, nothing here. But on the one thing that happens here is our assembly instruction jumps to our diversion and do the mathematical equation or calculation there and jumps back to our main early location and continues to execute, right? So no fun right here. now let's talk about how to actually increase the amount of damage to the enemy and no damage to the player. Now for that we can use the pointer comparison. Okay, so when we check our notepad here, so here this one, don't worry about this. So this is our base pointer and there is object for assigned to this pointer. All right, so this is the address that we are going to trace back. So this is the base and this is the offset for the player's pointer. Right, now we are going to use a simple conditional check against this pointer, or rather this memory address. So we basically say that if the EDX if the content of this address is same as the EDX register, notice only the EDX, not the content of the EDX register, then just do nothing and do the normal execution like nothing happened. But if it's not the same address, then reduce the health of some amount, then do the normal execution. So that's the that is basically what we are going to achieve here. So in order to do that, so let's do those steps one by one, right? So definitely we have to remove this every instruction. We have to remove everything, right? So here, if I maximize this window, if I check this address once again, this is lies in F248 offset from the base. So our base is 1C0000. This is F248. So 1C001C F248. So this is our memory section, data section. 001C F. All right. Now F. Now it's lies in F248. So this is F. So this is F and 10. This is F2. 48 is right here. So this is 40, 41, 42, 43, 44, 45, 46, 47, 48, right? So if I play this, or rather run this, you can see that memory address get some value here. Also notice that there will be another value in these addresses too. So this is the address of the player's pointer right here. How do we found that? Because of this offset, so we have the base, and the after F248 offset we can find the player's pointer. So this is the 248 offset from the base, so this is player's pointer. So notice this is 18CFOE00. basically this is in little endian, so the order is changed. Let's see now if I put a breakpoint here. So let's see, the value in EDX is same as this, right? So let me open this. So I'm going to shoot to the player. Notice the breakpoint hit. Now EDX is 00 0E CF18. So this is same as this address, but the only difference is the endian order. So the byte order is differs. So you have to use right to left reading order to decode the correct address. So this is 18CF0E00, but the EDX is 000E CF18. So if you read this reverse 000E CF18, so this is in the little endian order, so you have to read it backwards so you can get the address. So if we can write an assembly instruction to compare the value in EDX and the content of this memory location 001CF248, if those content values are same, that means the EDX, so this and content of this 001CF248 content is this value are same, then do nothing, don't decrease the health or do nothing, and just go to the just return from the function. But if it's not, so let me run this. So if I click here, now the EDX is 000E C000E CF18. I believe this is the address. 000E CF18. So this is your enemy and this is your player. So that's how data is arranged in the data section in your memory, right? So if the EDX now, as we can see, the EDX value is now completely different. So it does not equal to the content of 1CF248. So therefore, it's going to reduce the health from that object and do the normal execution. So that's what basically what we are going to do. So we do that modification and save another version. So we can increase, so we can implement that by step. Let's first try to compare the content of this memory address 1C so F248 to the EDX. All right. Now at this moment we are going to change the registers, and also the computation what we are doing with this instruction and register change will also affect to this flag registers. Okay, therefore it is a good idea to push everything, every register and full flag register to the stack before we do anything. That is because the program execution may get corrupted or may behave in some weird ways if we do not give the program what it wanted. All right, so basically what we it's like now we damage the program a bit, but this damage is negligible. But if I'm going to, let's say, change some value in these registers and some value here and there. And also, so if I do that thing, the registers, so if I debug this, so let me, so if when this when the EIP pointer encounters the return instruction, the registers all look like this, and this is our registers, this is the flag register. So if I do something inside this function and modified one of these registers, then there will be a problem to the caller function. So this is says that return to this one, though there will be a problem to previous caller. Alright, so previous caller may not expect the registers as it is, but it is safer to save the registers and return the registers as they were before to this our diversion. So you can push the registers couple of ways. So you can push individual registers using push EX, ECX, EDX, EBX, ESP, EBP, EDI, ESI and EDI. You cannot push or do anything with EIP. And once you done your function or your thing, you can pop the everything back reverse order. So you pop EDI, pop ESI, etc, etc. But and also you have to push the flag register and pop the flag register also. But there is a easier way. All right, push AD, push FD, and the reverse pop FD and pop AD. Push AD means push all the registers EAX, ECX, EDX, EBX, everything to the stack in one instruction. Pop AD is the reverse step. So the other instruction that we are going to use is push FD. So that is push the flag register, E flags rather, register. So everything from here to here pushed to the stack. So these are the carry flag, zero flag, and so on. And E flags, those are pushed to the stack. So let's start by pushing the relevant registers to the stack and do the computation. And if the memory address is the pointer is the player's pointer, then do nothing. And if if this is not the player's pointer, then reduce the health and let's get out of here. So basically, so let's start by pushing. So now first we are going to push the flag register. So push. Now the flag register is pushed. Now I'm going to push the every general purpose register. So push add. Now push add is completed. Now we are come to some question. All right. Here now let's knob everything because otherwise you get confused. Right now we have these two. So we basically pop now the popping order is pop AD and pop FD, right? The question is, how do we get this plus F248 address with our instructions? So this is the reason that there were many versions of the executable, as you saw when we start this video. So this is the reason. So multiple versions. So how we are going to do is somewhat tricky here, but we can do it. Okay. We can call a kernel function, also kernel method, to get the modules handle. So it returns the modules handle, but there is a problem with the modules handle. The problem is if you use like this. So if I get the kernel call like this, so I'm going to XOR the EX register with the EX register to 0 of the EX. So if I push the EOX to call the kernel function, so I'm going to push the EX, and if I call kernel 32s, get module A, right? So now I have the module handling EX register, so I can use that and I can add another F2 for it to get this memory location. But here's what happened. If I double click this one, you can see that there is a call to 77DECF41, right? So this is some kind like something like a static call. All right. So if I save this, so if I try to copy to the executable selection, so this is saved as. So you have to copy everything, otherwise your code gets jumbled up. So when you close your program and open this one again, this 77C23C41 may not map to the kernel 32 so get module handle A. If that's the case, your program definitely gonna crash. Okay. But here this works because at this instance, this function call maps correctly. But we cannot guarantee next time in the next run, this call, this location in memory maps to this get module handle A. What if it's mapped to exit Windows EX? Then when you double click the program, your computer gets shut down. So that kind of things can happen. But this method is not going to serve us any purpose. So I'm just going to knock these things out. But we can use another thing called like so let me maximize this window. But we can say this address, we can specify this address explicit like this. So I know that my EDX, so my EDX has the value, right? So since I didn't change the contents of the EDX register, so I have the value in the memory location in the EDX. So I can simply compare this like this. So if I use CMP, the contents of 001CF, so 001CF 248 with EDX. So I'm going to jump to some address. So right now I'm going to jump right here because the actual jump address is not yet calculated. So I'm just going to jump right here. So 001C, oops, 001C 4788 4788. So it's a short jump. There definitely this will be a short jump, no long jumps here. And so it jumps and do the mathematical calculation right here and go back. All right. So if I try to copy this to the executable, so okay, let's do this and let's see what happens. Okay, so now here it says if this is the same, the contents of this address, so this value, the content is this value, is same as the EDX, as we saw earlier. EDX is same. So this is the comparison. Then jump, if that is the same, then go to exit. Now if it's not the case, let's decrease the health as we did earlier. So I'm going to move the EDX. So this instruction goes like this. So now you see there is a ESP and EBP register move. So these are related to stack. So remember we pushed some stuff to stack. So let's pop everything, otherwise this is gonna screw up our program. So pop AD and pop FD. Remember you have to follow the correct order. And then we are going to move the ESP to EBP. Okay, now let's pop ABP and let's return. So I'm going and jump back to 11B7. So I'm going to jump to 001C11B7. So let me check the 11B7 address is correct. Alright, now it's correct. So let me save this. Alright, now since we are here, let's try to execute. Alright, now here I'm going to shoot to the player, right? So now instructions encountered, push FD, notice the stack here. So push FD, right, flag it, all the flags now pushed here. Now push AD, every register now pushed. You can see the EDI is pushed. After that ESI, so on so on, the registers are pushed. Now I'm going to compare. So if I get this one, you can see the compare the contents of this address with EDX. So EDX is this one, the contents of that address is also same. So this jump is going to be taken because the address is same. Now as you can see, nothing happens because I forgot to enter the jump address. Okay, now here this is the address that this is the only instruction that we change, so we can jump right here. So I'm going to jump to 47 AC. Let's see what happens. Right, basically what this does is it jumps to these instructions because we must go for pop AD and pop FD because we push those things, and we can exit. Right, now we are going to pop the FD. So ESP now changes, stack pointer is changed, and pop FD again. So again stack point is changed. Now we are going to follow the standard exit sequence, and we are going to jump back, and it's return instruction. Now program is running. So you cannot, I believe you didn't see anything. So let me remove this breakpoint. Right. So as you can see, the health is no longer reducing the player, but if I click enemy, the health is going to be reduced. But there is a problem here. I'm going to copy to the executable all modifications, and I copy all, and if I save the registers like this, I'm going to save this, and I'm going to use a different version. Let's say this is a flight hard-coded memory. Okay, so if I minimize this is my program. So let me get this one away so we can distinguish those. Okay, this is a new one. If I click it, looks like something happened. This is not the one. So notice now program is crashed. So this one is missing something. I don't know what happened there. So as you can see, if I click this, you see the program crash. Why is crashing? The problem is, if you check back our OllyDbg code, it says, if I copy to executable this thing again, if I copy all here, you can see this memory address is hard coded right here. So this is 1CF248. If this program loads in the same base address of 1000 again and again, and then this one is gonna work without any problem. But the problem is the operating system does not load this image, this EXE image, into the same base executable addresses and as with the same module addresses. So this base can be changed. You saw this in also cheat engine example also. You saw the address was the difference. So here at that time the address was like this. So as we know, if we go to a notepad, so if we minus 11B2 from this address, so this is one 248. So 248, so 13A00 F248 13A0 and 4 zeros. So it was, in this instance, it was 13A 4 zeros, and this is 13C 4 zeros. So like that, if the program is going to load in the same memory location, then it's not a problem. So then this one will work, then we can, you know, conclude everything and say goodbye. But here we cannot do that because it's not the case. So somehow we have to get the module base address and add F2 for it here, and then do the comparison, and then reduce the health in the enemy and not reduce the health in the player. Alright, so how we are going to do that? Now let me maximize this window. So up to now this one is okay, but here, from here again, we are back to square one. So how we are going to get the address? No matter what, the instruction pointers has the correct memory base address. That is why the instructions are executed. So this EIP is the one who responsible for executing the instructions. Alright. Now EIP register has the base address. You can see the base 001C, and 47A1 is the instruction that it was executed. So this one. Okay. Now if we can get the value from this address, then we are true. Okay. So but the problem is we cannot do like this. So this is not allowed because you cannot modify the EIP register directly. So if you could, then it will lead to some major security errors. So you can change the EIP. But in microcontrollers like PIC, you can change the PCL or PCLAT, both registers. So if you increase the PCL or decrease the PCL, your program counter let's go to backwards and forwards. But here in x86 assembly, this instruction is prohibited. Okay, but we somehow need to get the address of the base, and the kernel 32 calling is also not possible right here. Alright, let me show you what happened if we use the kernel call. Alright, so here I'm going to, as I already mentioned this earlier, but let me give you a taste of what is going to happen. Now I have the module handling EX register. Now I am going to add the EAX. So 0000 F248. So 1 2 3 4 4 bytes means that will be right. Now I'm going to do the comparison. So CMP, the contents of EAX. So EX has this value right now with EDX. Alright. Now I'm going to, if the jump is same, right now I'm going to jump right here 001C and 7B1. So oops, 001C 47B1. So this is a short jump. You can see the short jump instruction occupies less space here. So here for now I'm going to use this. Now if not the case, I'm going to move these values back. So make sure I'm not going to screw up in registers here. So EX and EDX. So I didn't touch the ECX earlier, right? No problem for me now. Now we have to pop the instructions back. So pop AD and pop FD and exit sequence. Jump back. 001C 11B7 1 2 3 4 4, that means that will be, or everything is correct. So let's see, can we run this? I believe this is running, so let's have a breakpoint here. Okay, I have this everything now correctly, so I'm going to debug one by one here. So everything pushed. Now I'm going to XOR, so I'm going for null and I'm going for kernel 32, right? So EX have the base address, so as I expect we can see that 001C 4 zeros, and I add 1CF 248. So again same thing happens, so I forgot to add the address, so let me add this. So pop at this in 001C 47B5 47. Now B is here, so it's going to be 475, and assemble this. So if I click it, alright, seems it's working properly, no problem whatsoever. So let me run this. So we have no exceptions. So if I shoot, nothing happens. If I shoot here, then it get killed. Right now, here we have, right now, let's save this as copy to executable, all modifications, and I'm going to copy all. Notice the call here, and I'm going to save this. Now I'm going to use a different name like kernel 32 mod handle. Alright, so this is my, so kernel 32 model handle, right? If I click it, it get crashed. So let me try to the debugger here. Let's see what happens, actually what happens here. Alright, so this is in break mode. So let's see again. Right, here we go. As you can see, this is our add byte PTR things. Alright, so you have this address, okay? So here we have 0EX. Now this call is not, right now is not mapped to kernel 32's call, okay? Therefore at this time this tries to calls to some unknown location, so basically there is no mapping to kernel or whatsoever, so that gonna cause us problem. So this program is going to be crashed, okay? That's why, so though you call this, so you push EX and call this one, and your next instruction right here, and your EX till 0, that means the correct kernel mapping was not there. If the kernel mapping was there, then this executable should have worked, okay? Otherwise, since the kernel mapping is not there, this executable won't work. So now we come to our last option, that is use this EIP register. But how are we going to use the EIP register in order to take our address? Alright, so how do we use? Alright, now when we use the method call using copying the EIP register to stack and pop it back to our one of our registers. So how we are going to do that? So in assembly or any programming language, so if you use a call instruction, so if I use call some here, so let me knock everything right now, so you can see I have plenty of space right now. So you see I have plenty of space. so no problem, I have plenty of space. So here, so I don't need this one either. So I am end up with these registers. Okay, so I have push FD and push AD, right? What if I call from here? I use a call instruction, so I call to some subroutine or some label. This one pushes current EIP into stack. Basically, the call instruction pushes EIP register into the stack, and from the call instruction, when I return, it pops the when the return instruction, it pops back to the EIP and start the execution from there. All right. So let's get our registers. Let's get our EIP register back. So we can use the EIP registers high order bits, high order bytes, high order 4 bytes means 2 bits, high order 2 bytes, high 2 bytes to get the base address, and we XOR and the lower order with the zeros. All right. So let's do that right now. So I'm going to call some dumb location. So let's call right here. All right, let's call, because we don't know the result address. Yes, so let's call right here 001C 47A1. So I'm going to call right here. Okay, after that, when I come back here, I have the address. I'm imagining I have the address in the EX. So I have the EIP register in the EAX register. All right. So assuming that, I am going to zero out the low order 2 bytes of the EAX register. So I'm going to AND the EAX with 0x. Higher 2 bytes are going to be ANDed with all ones, and lower 2 bytes are going to be ANDed with zeros. Right, so I'm going to assemble right that one, and now I have the base register, not the base register. Now I have the module base in the EAX register. So I'm going to add the offset F2 for 8 to the EAX, and now I do the calculation like the earlier. So I didn't touch the EDX value right here, so I can use the EDX. All right. So I'm going to compare the content of EAX with the EDX value. All right. If that's the case, I'm going to jump again right here. So I'm going to 001C. Use all this address later, otherwise it's going to create an infinite loop right here. All right. And if this is not the case, we use the same instructions like we did earlier. Okay, I'm going to copy the basic move here. So I'm going to use ECX to EDX, and now it's time to pop everything. And now I'm going to move the stacks and follow the exit sequence. And now I'm going to jump back to 11B7. Jump 001C 11B7. Right? Now I have to resolve 2 address right here. Now I have to resolve this one. So simply I am going for here. So 1 1, so this is b3, so this should be b7, and I'm going to resolve this one too. So here I have some space here. Okay, I'm going to resolve to c47a1 to c47c1, c47c1. All right, so this is my call right here. Now I can jump to here. Now here what I'm going to do is, now when I reached this position, my EIP register is pushed to the stack, so I'm going to pop back to that to EAX. Now since we use call instruction, we must return, but since I popped that value, the EIP register to EAX, if I use return right now, it's going to return to something else. Since we use this push FD and push AD, it will return to some corrupted location, so we end up with a crash. All right, now since we popped, the only thing we can do is now jump back to this address. Okay, sorry, this location. So the call is right here, so I'm going to jump back to the instruction below the call. So can we copy this? I don't think we can copy. So basically I'm going to jump back to this end instruction 001C. Let me check the jump instruction is correct. Right, jump is correct. Now it's ended. All right, let's see, hope this one won't crash. So let's try to run this. All right, program is now running. So let's see, now I'm going to shoot to the player. So I received right here. So here I'm going for step in. So I'm going to use, earlier I used F8 key, now I'm going to use F7. So here I'm going to do just now going to the call. So this is the call. Notice 001C47A7. This is the return address that copied from the IP register. All right, so we have to return right here, but I'm going to pop it. Now my EAX has this value, but I manually added the return address again, so I can safely go back. Now my EAX have the value of IP register that I popped from the stack. So I'm going to end this. Note, as you can see, now this has the base address as we received from the kernel, that tooth code. Now I have this address, so I can do the rest like same. So I am going to add this thing, and so I am going to end up with same things, right? So now the program is running without any problems. Let me remove the breakpoint. So notice the program is earlier also ran, but the issue was we were not able to save it. All right, so let's see whether this thing works. Now I'm going to copy all the modification. I'm going to copy all. I'm going to close this, and let's rename this as a fighter with EIP check. All right, so let me minimize this. So let this program run on side. Now here is our EIP check. No crashes, and notice the players health won't reduce, but the enemy's health is going to be reduced. So far so good. Now we have a program, we patched the program that only reduces the enemy's health, not the player's health. So here if I shoot to enemy, the health is reduced. If I shoot to player, the health is not reduced, so that is a good thing. All right, so now we need to increase the reduction rate, as I promised you last week. From one click from the players shoot to enemy, there will be 50% health reduction. All right. So in our program also, the earlier in the beginning I showed you our target program. There also we had a health reducing to 50%. All right. Now let's implement that in assembly level. All right. All right. So the calculation happens right here. All right. We may have to resolve this address later, and also we may have to resolve this address too. All right, because as we had instruction below this JE, this instruction may be eaten by our new instruction, so we have to recalculate the correct address location for these two calls. All right, so this jump and this call. All right, so what we are going to use is divide instruction in the assembly language, so div instruction. So to work with div instruction, so div work like this. All right, so let me, so assuming that you are dividing 8 by 4. All right, in assembly you are going to divide 8 by 4. All right, the answer is 2. All right, now the way it does in assemblies, we are going to use div instruction. All right, so what we are going to divide the top this first part of this division is going to be our EDX and EAX register. All right, the second part is any register. Let's say we are going to use DX register. All right, so our EDX going to be 0 here, and our EX is going to be 8. Now it's divided by BX is 2, and your answer is in EAX, and the remainder is in EBX. All right, sorry, EDX. So here the remainder is going to be 0 because 8 completely divided by 2. Oh, sorry, 4. Now here, since we use these division instructions, we have to move things around here a little bit, because EDX now in here EDX has the value to our pointer. Right, first let's now, since we didn't use EBX here anywhere, let's move our, since the division instruction takes the registers EDX and EAX, now let's move the current value in EDX to EBX. So I'm going to move EDX to EBX. Notice the assembly instructions are read as from right to left. Move EDX to EBX. Move EDX to EBX. Now EBX has the value in EDX. So I'm going to clean the EDX register. So XOR EDX and EDX. And I'm going to get the current value in enemy to the EAX register. So I'm going to move EAX, content of EBX. That is because right now we move the EDX to EBX, and now EDX is 0, but EBX, now the EBX is the register that contains our member location. All right, so the contents of EBX now is in EAX. Now our EDX is now 0. I'm going to move, so I used EAX here, I use EBX, and EDX is wanted, so the only register I am left with, it seems, that is CX register. Alright, so I'm going to move number 2, that means we are going to divide by 2, sorry, move CX, 2. So we are going to divide it by the 16-bit register. So 32-bit instruction now divided in 16-bit register. So now move CX to 2, and I instruct div ECX, sorry, not the RCX, it's a 64-bit. So once that I have new value in the EX register and reminder is in the EDX register, and so on. Alright, now the answer is in, since answer is in now in AX register, so I'm going to move, since my EBX is now still unchanged, so I'm going to move the content of EBX, so move the EX to content of EAX, sorry, move EAX to the content of EBX. Alright, now the enemy's health reduced 50%. Alright, now this is the instruction that's similar to this. Alright, now we are going to pop back, so pop AD and pop FD and jump back. The jump is 11B7 001C 11B7. Oops, forgot the jump instruction. Alright, let's see the instruction is correct. Alright, it seems it's correct. Alright, now I have to resolve some address here, so I have a JE short. Alright, now I should go for right here, so B7, it's going for, so pop FD, sorry, pop AD is in, okay, I think I forgot something, glad I saw it. I should use this one, I should follow the, let's copy this one to our notepad or something. Alright, so I should follow the exit instruction sequence. If I don't do it, everything's gonna be crash, and pop event just return. Now I am going to do the actual jump. Alright, so let me jump back. Alright, now let's resolve the addresses. So I have a call 74C1. Alright, now it's going to be 74CD. Alright, pop EAX, copy the value to EX. Alright, pop to EAX and jump back to 001C. Alright, this is the instruction address, 47A7. This is 47A7. Alright, I'm come here, call and jump back after popping, and the calculation. Alright, B7. Alright, so now B7, so I should jump from here. If the pointer is in the player, I should jump to right here. Alright, so it should be 1C47C3, so 1C47B7 goes to 1C47C3. Alright, so if the player correct, no, jump, pop, and exit sequence. I'm just going to jump back and back. Right, alright, let's go through one more time. So I'm going to push, call, and I pop the EX, so I have the value in the EX register, and I add the and with higher order, so I have the base and I add the offset I have compared with EX and EDX, so if it's same, no problem. So let's see if it's not the same. I move the EDX to EBX, so I clear out EDX, and here I fill the EX with the enemy's health and the divisor, and divide it, sorry, CX. 16-bit division is longer than 32-bit division, which was led to eat the instruction below it and set a NOP value, right? So if I continue run this, this will work, but enemy's health will not get reduced. Right now, what I'm going to do is I'm going to add this add the values back to our enemy's health and return from here. So I may have to recalculate these two addresses again. So let's do this right now. So I have the value in EX, as you can see earlier here. So I'm going to move EX to content of EBX. Alright, so now I'm going to pop with the order. So pop pop AD and pop FD. Right, after that I'm going to, after popping, I use these. Alright, and pop EVP. You see, this is this process is somewhat hectic. You have to do this carefully. That's what I told you. Right. Alright, looks like these have taken care of. Now I have to calculate these addresses. So our jump instruction again going to be some problem. You can see if I jump here, is jump in between address to this instruction. Alright, so move ESP CX minus 63, that's weird address. So it jumps right between these three instructions. Alright, so alignment is lost, so I'm going to realign. So I'm going to calculate this jump to here. So it's C3, now it's C4. So notice you cannot find the C3 here either. So it's C4 now. So if I jump this, now you can see working without any problem. Alright, okay, now pop AD, pop FD are there, and we are going out. So the call instruction, so here I'm going to copy this, or rather cut this, pop to the EX and jump back. So this one I'm sure nothing changed there. Everything under this as the one got changed. So this address also has a problem. So this should be resolved first. So this is pop EX is in CE, so CD is not here if you check closely. So C9 CE, no CD here, so it's called for CE. Let's see that one more time. Alright, popping, jumping back. Right, if everything correct, so go here. So if it is not the case, JE is going to be skipped. So EBX and EDX. Move EDX to EBX, so XOR and load the value divided by 2, these two instructions, and move the answer to in the EX to EBX the content and go back. Let's see, now I stop somewhere here. Alright, so I think this is going to be crash. But before anything happens, let me copy everything, because I'm not sure this one is crashed or not. So let's see. Let's see. Enemy health half. Alright. Let's see whether this one works. So enemy health half. So no crashes. That's relief. And you can see my health won't reduce, but enemy's health reduce. So yeah, no health reduction. 50%, 50%, 50%. From that 50%, 50, 50, 50, 50. Eventually, it reaches to 0. All right. So that's it. I believe that's because of this. If I run this. Alright, that program also runs without any problems. Glad. Anyway, we copied this. Alright, see here, that one also get reduced. Alright, so my health is no longer reduced. So that's how it's done. So that's how you patch your EXE using OllyDbg and the assembly instruction. So that's the bonus video, and that's the end of this bonus video. I hope you enjoy this. This is rather fun video, fun to mess around with assembly instructions and registers. So, and also this is though this is an easy process, so this everything is, if you get into it, it's easy. But only problem here is you have to keep track of every byte sizes stack and pushes and pops, so, and mainly the flag registers. So if you take care of that, and if you do the pushes and pops accordingly, and then you are in no trouble. You have fun of doing assembly programming. So that's the end of this today's bonus video, and I hope that you enjoyed this video. So once again, this video is also some bit advanced here, so if you have any single question, please do write in the comment section. I will answer to those questions in the comments or by sending an email. Alright, so as I mentioned earlier, I want you to get this thing crystal clear. So if you have any questions, you may have questions or you may not have. If you come across any questions or if you have any difficulties, please do ask from the comments section. I will do reply. So with that being said, I hope you enjoy this video, and thanks for watching, and thank you very much. And don't forget to subscribe to my channel. It's Fun Tech with Hashan, and give a thumbs up and give a like to this video, and click the bell icon in our channel to notify when I uploaded a new video. So goodbye, have a nice week.